What's a Ramjet rocket? Ramjet rocket is a kind of type of propelled system which is used for high altitude and very high speeds flights. So the best Mach number, which is the most efficient for the Ramjet rocket, is from 2.5 to 4.5 Mach speed. And what's interesting really for the Ramjet rocket, because it doesn't have any more impacts. Because of that, we have a problem. You cannot start the engine from the zero point. You need some booster. So we can assume that we have a booster on the engine. It propelled to the Mach number about 3, and we have, because of the shockwaves produced by the supersonic flights, we have a compression inside. So you don't need a compression system. So our assumption is that here that we have isentropic system, and also we have a steady and visit to the airflow. So our kind of main objectives of this whole project is to design the geometry of the whole rocket. We have 3 main parts called inlet, combustion chamber, and nozzle. We'd like to more stuff about them. And the whole rocket has to sustain flight at 10 km and altitude of 10 km and Mach number of 3.
So the inlet is the front part of the engine, where the air comes in, and we have a supersonic free stream airflow of Mach number 3 outside, and inside, at the exit of the inlet, high pressure compressed air, which we assumed would be traveling at a speed of Mach 0.3, which is required for combustion. So how does the inlet compress the air? Well, in this image, you can see 2 ramps. The first ramp at an angle of A1 from the horizontal plane of the inlet. This ramp creates a shock wave converging at the cat with a shock angle of S1. And the second, likewise, creates a shock wave called S2 here that also converges at the cat. These 2 shock waves converge at the cat for maximum efficiency.
The convergent nozzle is the component in the end of the Ramjet engine. It converts.
Can you use the mic, please?
As I said, convergent nozzle is a component located in the end of the Ramjet engine. It converts subsonic flow to supersonic. The pressure in the throat section must be higher than the pressure in the deck section, since we want to create a flow that moves towards the exit section. We use the small engines. Here you can see the convergent engine. It is the angle between the horizontal plane and the convergent part. And the same here. This angle is between the horizontal and the divergent part. We use small angles because we wanted to decrease the drag, and here we wanted to avoid turbulence, which minimizes the thrust.
So these are the equations we use to get our results. But instead of explaining the equations, we'll just skip straight to the results.
What about our results? So we show you here the 3 different graphs. On the first graph, you can see the ratio of the entrance area and the area where we have the normal shock. So we can see that how our first deflection angle, which Federico explained, the A1, you can see here how that our entrance into throat area ratio decrease. The usual and the most efficient of the Ramjet engine has about ratio about 4. So our main part of design is to sustain the pressure inside the combustion chamber or at the exit of the inlet. So here you can see how our pressure at the exit of the inlet changing the first deflection angle. So, but what's more important that you can see that how this is decreased. But these numbers are really higher and enough for our combustion. But if you make a steeper ramp, the other oblique shock which we have is gonna turn the pressure, this pressure more down. So we're not gonna have enough pressure for our combustion chamber. So the results on this section.
So here we have a 3D model of our engine with the inlet starting here and ending here, and then also starting here and ending here. Thank you to Dylan for making us this model. So we chose angles of 10 degrees and 8 degrees with respect to the airflow as our deflection angles. And after every ramp, every deflection angle, you have an oblique shock wave. And after every oblique shock wave, you have a decrease in Mach number velocity and an increase in static pressure. As well as shock wave, we also have a decrease in flow area in this section, where here, where the area is at its minimum, we have the throat and a normal shock wave, which has the purpose of converting the flow from the supersonic regime to the subsonic regime without too many total pressure losses. So our geometry was succeeded in converting the supersonic flow of Mach 3 to a subsonic flow of 0.3 here. We had static pressure well over our minimum of 2 atmospheres. We got about 9 atmospheres. And our pressure losses were only about 5%, total pressure losses, which is good since we limited ourselves to 20% as a maximum.
We also succeeded to accelerate the air-fuel mixture to a Mach number of 2.9. We succeeded to make the pressure in the throat higher than the pressure in the exit section, and to create a slow air-fuel flow to move towards the exit section. We received a result of 31 kilometers of thrust. As you can see in this model, the diameter this loss is half a meter, and the total length of the nozzle is 1.23. That is good because we limited ourselves to a meter and a half. The total length of the whole Ramjet engine is about 3 meters.
So just to recap, we succeeded in creating a geometry that was able to get the pressure we needed in the combustion chamber and the velocity we needed at the exit of the nozzle to create thrust. Our assumptions agreed with our expectations and especially with our results. And the 31 kilonewtons of thrust were opposed to only 26 kilonewtons of drag. So we got a good net thrust of about 5 kilonewtons. Finally, we'd like to thank Vaynshtein for being a great mentor and guiding us through this project. We'd like to thank Dylan for creating our model. And we'd like to thank Mr. Stern and the Gilbert Foundation and all the Technion staff, and especially all of you guys for listening to us and for your attention. Any questions?
Yeah. Could you go back to the slide where you have the ramps?
Yes.
Yeah, there. Okay, so why do you have like a completely flat ramp and
So you just want, not every model not every geometry has 2 oblique shocks. Some have 1. We actually have 3 shocks in total, including the normal shock. But having straight ramps is the most efficient way to create it. Any other questions?
Is it common to use the assumption it's an isotropic flow, the supersonic?
Do you want well, having an isotropic flow means that every process is adiabatic, so we don't have any, energy or heat exchanges in the engine. So, for example, for calculating temperatures, total temperature is basically constant throughout the entire engine. Also, we have for an isentropic flow, we have we assume a reversible flow. So again, entropy, net changes in entropy are always 0. So for our purposes, yes. Any other questions?